So the last video on chapter 8 and kind of an introduction to chapter 9, what I want to do is I want to talk about why the residue is the most important term in the Laurent series and why really it's the only term that we need in order to evaluate some integrals. So let's say that I have a function f, and I'm just going to for sake of argument, assume everything is nice, and we'll work out the actual details going forward in chapter 9. But let's say that I have a function f and it's got a Laurent series, a sub n times z minus z naught to the n goes from 0 to infinity, plus the negative coefficients, so the negative powers, b sub n z minus z naught to the negative n is n goes from 1 to infinity. Okay, so let's say that this is what we have. So this is our function. And what I want to do is I want to look at what's the integral of our function f over some circle centered at z naught of whatever radius, say radius 1. Okay, I shouldn't say radius 1, just make it radius r, but I want to do it so that it's, we're talking about isolated singularities. Let's make it so that this is a circle that only contains the singularity z naught. There's no other singularities in there. Otherwise, we'll have to do some other stuff. But that's fine. What this is going to mean is that this is going to be the integral of the following sum here. So this is going to be the integral over this circle centered at z naught of radius r of a sub n times z minus z naught to the n, and we're going to sum this from 0 to infinity, plus the sum from 1 to infinity b sub n z minus z naught to the n, okay, dz. Now, one of the exercises that we did way back when, which turned out to be, which is going to be key here, and this is something that I've already talked about, is that if we integrate over a circle, say centered at some point z naught of radius r, and we look at z minus z naught to the m, remember that this is going to be 2 pi I if m is equal to -1, and it'll be 0 otherwise. And so if you have z minus z naught to the -1, that's going to be the only value that picks up this 2 pi I. All the other integrals will be 0 because all the other integrals will have an antiderivative. The circle is closed, and therefore the integral will be 0 for reasons that we've talked about in chapter 4. However, at -1, you don't have a nice antiderivative because, again, for reasons that we talked about, if you're looking at 1 over z minus z naught, that integrates to log, which has the branch cut, and then things fall apart, right? You don't have that normal antiderivative that's holomorphic over any disk containing this point, right? Because you're missing the branch cut. So the moral of the story here is that the only integer exponent that's going to matter is when m is equal to -1. Well, lo and behold, what does that mean over here? What's the only power of z minus z naught that's going to matter, that's going to integrate to anything other than 0? What's going to be, of course, when z minus, it's going to be when you have the exponent of -1. And that's exactly why that b1 term is the most important term there. So this is just going to be the integral. So this is just going to be the integral where you have z minus z naught, we had a b1 to the -1 dz, because all of the other integrals are going to integrate to 0. Now, one thing that I just did, which is sneaky, which maybe you can argue with me about, is that I just interchanged the sum and the integral, but we can do the usual games and find a closed annulus where the Laurent series is uniformly convergent, and then mix the sum and the integral, and then everything is fine. But I did just do a little bit of sneaky stuff there without making it look sneaky. But anyways, the only term where anything's going to matter is that when the exponent is -1, and you can factor out the b1. So you're going to end up with b1 times this integral of z minus z naught to the -1, and that's going to be b1 times 2 pi I. So in other words, if you integrate a function f over some circle centered at z naught of radius r, what this is going to be is it's going to be 2 pi I times the residue of f centered at z naught. Okay, this is kind of our first glance into the residue theorem. Okay, so we'll say lots more about this in chapter 9.